In example 4, we're going to use the graph of f to sketch the graph of f prime. Okay, so this function is piecewise linear, so I can use exact values. So the slope over here is -1. Then the slope in the next piece is, looks like +1. Then the slope in the third segment looks like -1. And the slope of the last segment appears to be 1/3. So I'm going to try to make my graph like exactly piecewise linear. And so I'm going to say that's where -1 is on y, that's where 1 is, just to give me some room for putting 1/3 on there as well. And then the x scale, I really just need to know where -2 is, where 0 is, where 2 is, and that would be what, 5? There we go. All right, so we're going to draw something over here that has a slope of -1 all the way until -2, open circle, because at that point the slope was undefined. Then a slope of +1, so open circle again, slope of +1 through to 0, open circle. Then the next piece, starting at 0, going to 2, has a slope of, I forgot to write the negative there, sorry, I meant to write it, -1. And then the last piece, the slope is 1/3, open circle, over, and it does continue past 5, so we'll just have an arrow at the end for both of these ends. Okay, so that is what the graph of this derivative would look like. It has 1, 2, 3, 4 different segments, piecewise derivative graph. Don't draw them wrong again, please. Okay. All right, example 5, we're going to match the graphs of the function a, b, c, d with the graphs of their derivatives. Okay. C is the only one that has a negative slope, so C is going to have a negative value. So I know that this graph over here is C. A, B, and D all have positive slopes, and D is a lower value. These two look parallel, so they're going to have the same slope, the same derivative, and it's a higher value. So A and B will both have that higher value, the higher positive value, and D is going to have that lower positive value. Now again, because there is scale here, we can see that the slope is up 1/1, the slope is 1 for both of those, and the slope is up 1/2, the slope is 1/2 for both of those, so that helps us, that's also 1/2 as a y value. Okay? Sorry, I didn't realize that was a little bit off the screen, but hopefully caught all of that. Let me push this up. The last example for this section, example 6, we have the graph below. Find the x values in the interval for which f is not continuous. So f is not continuous at x equals 1 because you have your jump discontinuity right there. Find all the values where f is not differentiable. If it's not continuous, it's certainly not differentiable, so it's not differentiable at x equals 1, but it's also not differentiable at x equals 2 because of this sharp turn right there. So differentiability is a more restrictive condition than continuity.